Domain and range help us describe where our function is defined. So the domain's going to describe all of the possible input values we could have. So really domain focuses on x, and the range describes the set of all possible output values, which really focuses on y. So let's talk about a case in context, and then we'll go through some examples with given graphs. How do we find that domain and range? And then we'll end with the different types of functions we could come across and how we would find the domain, just the domain for those cases, not the range. The range really relies on the graph. Sometimes there's some tips and tricks, but in terms of algebraically, we'll just focus on finding domain from different types of functions. All right, so this word problem here, we have the population of a small town in the year 1960 was 100 people. I'm going to go ahead and start highlighting here. So 1960, there were 100 people. Since then, the population has grown to 1,400 people, reported during the 2010 census. Choose descriptive variables for your input and output, and use interval notation to write the domain and range. So we need some variables. We need a variable for input and output. Our variable for input, or x, is typically something that is independent. It's working independent of things. So for this case, we have two values. We have population and time, or year. Now, population might be relying on something, so it's not really independent. It could be depending on the amount of time that's passed. It could be depending on the growth rate or growth decay that's occurring, whereas time operates independently. It's just moving forward. It's not relying on anything. So in terms of input and output, this amount of time, or let's say year, would be our input variable because it's independent. And then let's go ahead and call that t for time. So our input variable is year, which is time, and then output is going to be our dependent variable, which is that population. And let's go ahead and call that the variable p. So for the number of people. Okay, so domain. What we're doing here is talking about how is time restricted here. What are the possible times we're going to see for this description? So we're talking about how it's starting in 1960, ending in 2010. So for our variable t, what we're going to do is we'll say 1960 is less than or equal to t is less than or equal to 2010. Since we're defined at 1960 and 2010, we'll include those endpoints. So in interval notation, we'll use square brackets. So square bracket 1960, comma, 2010, and square bracket. Now for the range, we're describing our possible values for population. So what we see is we started with 100 and then went up to 1,400. So 100 is going to be our lower value, and we'll say that's less than or equal to p is less than or equal to 1,400. And this is definitely working on the assumption that it just increased directly from 100 to 1,400. We'll assume there weren't any major drops or increases in there that goes beyond those values. So in interval notation, we're starting at 100 with a square bracket, comma, 1,400, using a square bracket because we're including those endpoints. So that's how to think of domain and range in terms of a word problem. Now with these different graphs, this first graph, what you'll see is that these are discrete coordinates that are plot here, and what that means is just separated coordinates. We have -3, -2, -1, -2, 2, 4, and 5, -3. They're not connected in any way. So describing the domain and range, what we're going to do is, in this case, just list values. So what we're going to have is for domain. For this, we'll use set notation. So we're going to use that kind of curvy bracket. And for domain, we're using the x coordinates. So we have x equals -3, -1, +2, +5. So we're just going to list those in the set. So -3, -1, 2, 5. And then close that set with those brackets. Now for the range, we're going to do the same thing. So for the y coordinates, we have a -2. We have -2 again, but if we're making a list, we don't need to repeat it. We also have a 4, we have a -3. So if I go ahead and list these, and I'll go ahead and make them increasing, so I'll go -3, -2, I'm just going to list that once, and then 4. So we end up with a list of values for those inputs and outputs. So this will happen when you have just discrete coordinates graphed, like a scatter plot. You'll just have a list of possible x and y values. For this next graph, we have a linear function, and it's starting at x equals -3 and going to +4. Now at -3, so we're at the coordinate -3, -4, we have a closed circle, and then at +4, +2, we have an open circle. So it's telling us a bit about how this function's defined. So with domain, since we're focusing on the x values, that's our horizontal coordinates, so it's how we move left and right. Something I like to do with these for thinking of domain is kind of starting on this left-hand side and scanning across the graph and thinking about when our function's defined. And really, I'm going to kind of stick along this x-axis here. So if I go along the x-axis, and I'll start out here at -5. At -5, there's nothing. -4, there's nothing. -3, our function starts to be defined. And with a solid circle, so x equals -3 is defined. And then our function continues on to be defined all the way until we get to x equals +4. And at +4, we have an open circle. So what that tells me is that we're defined all the way up until +4, but not including it. So our function is defined at like 3.9999999. That's good. But as soon as we hit 4, no longer defined. So in terms of domain, I want to describe this interval of starting at -3 and including -3, and then going up to +4, but not including +4. So what I'm going to do is use a square bracket with -3, comma, +4, and then I'll use a curved parentheses to show that we're not including that endpoint there. Now for range, I'm going to do the same thing, but along the y-axis, and this is how we move up and down. So what I'm going to do is start kind of like at -infinity almost, but really on this graph, it's more like I'm at -5, and we're not defined, but then when we get to -4, our function starts to be defined. And that's with our solid circle there at -3, -4. So with that y coordinate of -4, we're defined, and then our function's going to be defined all the way up until we get to +2, where there's that open circle at 4, 2. So at +2, we're not defined, so I'm going to use an open circle. But if we were at like 1.999999 for y, our function is defined, but it's just at 2 we're not. So for the range, our lower value is the -4, and we're including it. So I'm going to do square bracket, -4, comma, +2, and then use a curved parentheses to show we're not including that +2. All right, this function here is made up of a lot of linear pieces. So for domain and range. So for the domain, if I think of starting at like x is -infinity, so out here on the right-hand side, what we can see is an arrow on our graph where our graph is continuing on forever. So basically our function is defined all the way across our graph, and when we reach the right-hand side, like going off to +infinity, we can see another arrow on our graph which tells me it's continuing on. So basically we're defined for absolutely any x value. So x can be anything. So x is all real numbers. In interval notation, what we could do to describe this is from using our parentheses, -infinity to +infinity. Or this is the case of x is all real numbers. All right. And then for the range, now for this one, our range, if I start down here at like y is negative infinity, you can see our function isn't defined down here. So if I start moving up, our function starts to be defined at -2. There's this kind of lower point at 5, -2. So our function starts to be defined there. I'm going to use a solid circle to say at -2 are defined. And then our function's defined all the way up. And then what those arrows are doing at the ends of our graph, they're continuing upward. So y is going to be defined all the way up to positive infinity. So for the range, we're starting at -2 and including it. So I'm going to use a square bracket, -2, and then comma, and then we're going off to positive infinity and close that with parentheses. And our last graph here, so this is a rational function. So our rational function will have spots where our function's undefined. In fact, let me even draw our vertical asymptote here. So in terms of x, what I'm going to see is we're defined out here all the way out to negative infinity. Our graph is going to be defined, it's defined, but basically we're just going to skip over that vertical asymptote at x equals +2. So I'm going to have this hole in the domain at +2, but then my function continues to be defined all the way off to positive infinity. So this is where we use that interval notation that is for skipping over a single point. So our domain is going to start at negative infinity. It's going to go to +2, and then I'm going to use those curved parentheses to say, but we're not including 2. And then union, that symbol that's a big capital U to say or, we can be starting at +2, again with a curved parenthesis to say we're not including it, to go to positive infinity. So this notation here is describing that we're defined absolutely everywhere except for +2. Now for the range, we're going to have a similar scenario. What we'll have is y is defined all the way at negative infinity, going up and up and up. But then at +1, we have this horizontal asymptote, and our graph doesn't cross that horizontal asymptote. So at y equals +1, we're going to be undefined, and then going off to positive infinity. So I want to use that same notation, but describing how we're skipping over +1. So I'm going to go negative infinity to +1 using a curved parenthesis, union +1 with a curved parenthesis to positive infinity. Say we're just going to skip over that +1. All right, so that's reading it from a graph. Now let's talk about algebraically. And what we'll need to do is when we're finding the domain algebraically, we need to think about what type of function we're working with. So a linear function would be our y equals mx plus b. Quadratic function would be a y equals ax squared plus bx plus c. Radical function is going to have a square root involved. A rational function is going to be a fraction, so you'll have a function in the numerator, function in the denominator. I'll call that p of x over q of x. And then a mixture can mix any of those together. So if you have a linear function and you need to find the domain, luckily it's nice and easy because when we graph a linear function, we are defined absolutely everywhere. And again, we're only focusing on domain here. So with a linear function, you can plug in absolutely anything. So the domain for any linear function is all real numbers, so negative infinity to positive infinity. For quadratic, that's also true. If we draw a parabola, you can plug in absolutely anything into a quadratic and you'll get an output. So domain for quadratic functions is also negative infinity to positive infinity. Now, with radical functions, we start running into issues in terms of what we can plug in, because basically we cannot take the square root of a negative number. So whatever is underneath this square root number, or sorry, the square root symbol here, we need to make sure that whatever is underneath has to be more than or equal to 0. We can take the square root of 0, we can take the square root of positive numbers. So this is going to be a restriction on our domain. So here we have this example of f of x is equal to the square root of x plus 4. So x plus 4 is all underneath this radical here. So what I need to make sure is that when we simplify that x plus 4, it has to be more than or equal to 0. So what I would do is I'm going to take that x plus 4 and say that has to be more than or equal to 0 and solve that inequality. So I would subtract 4 from both sides. So x has to be more than or equal to -4. So for the domain in this, using interval notation, if x has to be more than or equal to -4, I would use a square bracket starting at -4 and then going off to positive infinity. So radical functions, take whatever's underneath the square root, set it to more than or equal to 0, and solve for x. For rational functions, with rational functions, we're going to be restricted by the fact that the denominator cannot equal 0. So whatever the denominator is, that is not allowed to equal 0. So for this example, we have 2x plus 1 divided by 3x plus 4. So I can basically just ignore that numerator there, but this denominator, the 3x plus 4, I'm going to write that down. So 3x plus 4, and then does not equal 0. So that denominator cannot equal 0. And what I'm going to do is solve for x here. So I'm going to subtract 4 from both sides. So 3x cannot equal -4. Divide both sides by 3. So x cannot equal -4/3. So there's our restriction there. If I want to write this in interval notation, what I would use is that notation for skipping over just a single value. So we could be from -infinity all the way up to -4/3, but not including -4/3. So we'll do a union with -4/3 to positive infinity, all using those curved parentheses. All right, a mixture of the two. So with this one, this is 2x plus 1 and then divided by the square root of 3x plus 4. So with this one, there's two pieces. I have the radical. So I have the idea that this 3x plus 4 underneath the radical, that has to be more than or equal to 0. I also have this idea that the entire denominator here, so the square root of 3x plus 4, is not allowed to equal 0. Now this one's a nice one to combine together, because what essentially will happen, like this square root of 3x plus 4 cannot equal 0, if I square both sides of that, we get that 3x plus 4 cannot equal, and then 0 squared is just 0. So what we can do is just take this 3x plus 4 that we got here, and where we were saying that it has to be more than or equal to 0, what we're going to do is just take away the equals. 3x plus 4 has to be strictly more than 0. Since that denominator cannot equal 0, we just lose that possibility where it can equal 0. So we'll solve, subtract 4 from both sides, so 3x has to be more than -4. Divide both sides by 3, x has to be more than -4/3. So for our solution here, we're going to start at -4/3, go off to infinity, and we'll use curved parentheses since we're not including the -4/3, and then infinity always has those curved parentheses. All right, so those are the different ways to write our domain and range. Again, for these kind of solving algebraically, we'll just focus on finding domain, not range.